Alright, so this video we're walking through Check Your Understanding 1.7, where we're trying to estimate the height of the Earth's atmosphere. So we're given the mass of Earth's atmosphere. And it is on the order of 10 to the 19th kilogram. We're also told to assume that the density of Earth's atmosphere is 1 kilogram per meter cubed. And we want the height. All right, so looking at this, the first thing I would do is dimensional analysis. The dimensions of what I want, height, is meters. And I don't have, in the two pieces of information, I don't have meters directly, but I do have meters to a power. So that'll get me a little bit closer to what I actually want. So with these two pieces of data, what can I do? Well, again, I'm going to do some dimensional analysis. Density is kilograms over meters cubed. So that means I can make up the formula for density. It's kilograms over meters. Kilograms is mass, so density must equal mass divided by meters cubed, and that's volume. So there I have made my equation for density. And I've got mass, and I've got density, and that means I can get volume, which gets me a little bit closer to meters, a length. So let's go ahead and rearrange this equation to solve for volume. So I'm going to multiply both sides of the equation by volume. Those two will cancel. I'm left with volume over here, and then I'm going to divide both sides of the equations by density. So density cancels as well, and I'm left with volume equals mass over density. And then I can plug in my mass on the order of 10 to the 19th kilograms. I can plug in my density, 1 kilogram per meter cubed. I've got a fraction down here. That's the same as multiplying by the reciprocal if we divide by a fraction. Remember, the reciprocal is you just flip the two sides of the fraction. So I'm going to rewrite this as meters cubed over 1 kilogram. That's the same thing as dividing. So I've done my dividing. I can stop that. I can see the kilograms will cancel out because I'm multiplying and then dividing by them. And that means my volume is 10 to the 19th meters cubed, at least in order of magnitude with this assumption for the density. All right, so I've got a new bit of information. Volume is 10 to the 19th meters cubed. So it's still not what I want. I want the height. I've got some volume, so I need to figure out what's the connection between volume and height. Well, probably an area. Volume equals area times height. Volume is in meters cubed, height is in meters, area is in meters squared, so this equation at least works out as far as units are concerned. So what area might I be interested in? Well, we've got the Earth, and then we've got its atmosphere around it. So this guy's a sphere, the Earth is, roughly speaking, and the atmosphere also is a sphere. And so let's do the surface area of a sphere. And from a previous problem, we know that that is 4 pi r squared, the radius of whatever sphere we're using. Now we know that this is not quite correct, because the surface area on the Earth's surface is going to be smaller than the surface area at the top of the atmosphere, because you can see the radius here is a lot smaller than the radius here, and thus the surface area is going to be bigger when you have a bigger radius. But it's a good estimation. So that means in order to get the surface area, so we can divide the volume by the area to get the height, we need to find the radius. And a previous problem told us, well, we didn't get the radius, but we did get the diameter, which is 2 times the radius, and they said the diameter of the Earth was on the order of 10 to the 7th meters. So we're going to divide these two. We're going to divide the diameter by 2 to get the radius. So that is going to be, let's split this 10 to the 7th up into 10 and 10 to the 6th meters. So we can divide one of those 10s, this guy, by 2. And we'll get the radius is 5 times 10 to the 6 meters. All right, so now we have the radius, so we can plug it in here so we can get the surface area. If we have the surface area and we've got the volume, we can get an estimate for height. All right, we're well on our way. Okay, well, surface area, that is going to be 4 times pi times 5 times 10 to the 6 meters squared. And we're doing an estimation. Already we've made a whole bunch of assumptions, and so we really don't want to keep a whole bunch of numbers that are more precision than we need, because they are less precise than the assumptions we've already made. So 4, we'll keep that for now. Pi, well, that has a whole bunch of decimals if you do it exactly, but we're only going to do it to one significant figure, so pi becomes 3. And then we will square everything inside of here, so 5 squared is 25. 10 to the 6th squared is, well, we multiplied the exponents, so that is going to be 6 times 2, that is 10 to the 12th, and meters squared. All right, so this is kind of nasty for just on-the-fly board math. 4 times 3, that'll be 12. 25 times 10 to the 12th, sorry, meters squared. All right, I'm running out of room, so I'm going to erase up top here so I can get some more room. Oh, we need to keep the volume. We're going to use that still, 10 to the 19th. We want the height, so I'm keeping that. All right, so surface area. We ended up with 12 times 25 times 10 to the 12th times meters squared. And we are going to do some rounding because we only want that one significant fig. So 12, that would round down to 10. 25, that would round up to 30. Don't need to do anything with the 10 to the 12th or the meters squared. All right, so I'm going to erase all of this. I'm going to write my volume in down here, 10 to the 19th meters cubed. Once I've done that, I can erase this. Now I'm going to write my surface area. Let's make it a little more concise here. 10 times 30 is 300 times 10 to the 12th meters squared. That is going to be 3 times 10 to the 14th meters squared. All right, we're going to write that in here. 3 times 10 to the 14th meters squared times height. And then we'll divide by 3 times 10 to the 14th meters squared. Do that on both sides so the equation remains true. And we will have height equals, well, this is the same as having a 1 here, so we'll do our scientific notation term. 1 over 3 times 10 to the 19th over 10 to the 14th. That is going to be 10 to the 19 minus 14, or 10 to the 5th, meters cubed over meters squared. That is going to be meters to the 3rd minus 2, or just meters. Yay, those are the units we're looking for. This will become to 1 sig fig, 0.3 times 10 to the 5th meters. And then we can write it in true scientific notation. 3 times, we have to steal one of these 10s to make this a 0.3 to a 3, so that leaves us with 4 of them. 3 times 10 to the 4th meters, or 30 kilometers. And then it asks us, is this an over or an underestimation? Well, we know that we got the surface area incorrect. We assumed that the surface area was a lot smaller than it actually was. And since we're dividing by a smaller number, you'd think that would give us a bigger number. But it turns out a bigger assumption that we made was that the density was uniform. It was 1 kilogram per meter cubed. And the density, redraw our little Earth here, the density decreases the further you get away because the Earth's gravitational pull gets weaker the further you get away. So it turns out we're off by about an order of magnitude here. It's more like 300 kilometers tall. But that gets us pretty close for, as you can see, not doing very much fancy math and making a lot of assumptions. So that's how, in general, you do guesstimation problems.